necessarily help you, but it also just necessarily like diversity.
Okay. So we are ready to finish up with our understanding of mean arterial pressure and its regulation. So I heard some talking. Hopefully everybody at least jogged their memory on compliance. Part of why I picked this one out is this the first time I had to learn about compliance. I found it kind of tricky, so I think it's worth practicing a little bit. Anybody want to tell me anything about compliance? That's about compliance. Okay. The other reason we're talking about this now is compliance will continue to be something that we think about as we think about the lungs in our next unit. So this is a concept that affects a lot of different parts of your body, not just your vasculature, but fundamentally for our purposes for shorthand, we can really just think about understanding high compliance versus low compliance and sort of the physical properties that would be related to that. And so two things we've talked about with low compliance. We've talked about the fact that our arteries have low compliance compared to veins. And we talked last week about drops in compliance in the veins and how those drops in compliance mean essentially that we're having an increase in venomotor tone and it's helping us return more blood to the heart. So those are what we're relating compliance to in our cardiovascular system. So is this stuff. So our veins usually have pretty high compliance. If something is compliant, this means that we can hold a lot of volume for a given pressure, or vice versa. At a pressure, we have high volume. That's why we think about the veins as our volume reservoir. So one of the things that we can vary with our veins are the compliance. So that drop in compliance is a reaction to increased sympathetic activity, ultimately increases mean arterial pressure because we're returning more blood to the heart, increasing cardiac output. So our overall relationship defining compliance is about that relationship between pressure and volume. So shorthand, right? The high curve, high volume, high compliance, low curve, low volume for that pressure, low compliance. Okay. So here were our arteries with their low compliance, which is actually helpful for us in the arteries because low compliance means high pressure. So this is like a trade-off between volume and pressure in this relationship. Cool. So last time we had started thinking about how we regulate our mean arterial pressure, which is essentially our blood pressure averaged out over time. Okay, so we talked about the fact that we can have short-term regulation and we can also have long-term regulation, whether we're thinking about sort of seconds to minutes, kind of like reflexes. It's going to be our short-term regulation, compensation immediately. And then long-term, we can have adjustments kind of system-wide. Okay. So we'd started out by thinking about this short-term regulation. This is where we're going to spend most of our time because we want to understand what happens day to day. This is going to happen all the time. Like every time you stand up, you actually have to adjust your blood pressure a little bit. So we talked about the pieces that we're going to be thinking about. So we have a mechanism for homeostasis. So we're going to have a sensor or a detector, which is our receptor. So our baroreceptor, right? In the slides, right? But the baroreceptor is sending a signal up to your brain. In this case, your integration center is in your medulla oblongata. Okay. We then send signals back out to the body. Right? So we're sending signals back out, and that control is happening with our autonomic nervous system. Okay, so we're thinking sympathetics, parasympathetics, and then our effector organs. are our heart and our blood vessels. Okay, so we know that both our veins, our arterioles, we've talked about variation with those, so we're thinking about those, right? So heart, talked about veins just now in our little review of compliance. We talked a lot about resistance with the arterioles. All right, so these are going to be some of our major factors. So blood vessels in general, I'm just picking out some of the ones that are going to be most important that we can vary. Okay. So overall, when we're thinking about mean arterial pressure, we also talked about the factors that determine what our mean arterial pressure is going to be. And we reshaped that flow equation. So that flow equivalent to a change in pressure divided by our resistance. I'm not going to walk us through how we reshaped that because we spent some time on that last time, but overall, we reshaped it until we got our mean arterial pressure is going to be dependent on our stroke volume times our heart rate times our total peripheral resistance. So we're focusing on anything that can affect any of these factors in order to adjust our mean arterial pressure. So this is about where we left off. All right. So when we're thinking about neural control, this is the main way we're doing this short-term regulation. So when you stand up and get dizzy, this is what's supposed to kick in. We're looking for that detector, that baroreceptor, going to an integration center, a controller, and out to your heart and blood vessels. And that should be happening pretty quickly. And in that video we did on the first day, talking about that patient who has a lot of falls, right? This is part of the system that's going wrong for him, right? Is this regulation of blood pressure and therefore regulation of all the things that depend on blood pressure, that depend on you getting consistent oxygenation, consistent blood flow. Okay. So since we're thinking about neural control, that means we're thinking about nerves, right? That's what neural means. And we just covered that the nerves that are sending out our signals that are going to be really important for this mechanism for homeostatic control are our autonomic nerves. Okay. So we're going to have autonomic nerves that are going to be going out to our cardiovascular effector organs, affecting those three factors that we're interested in: the heart rate, the stroke volume, as well as that total peripheral resistance. So we have our two branches of the autonomic nervous system, and both of them can have effects. And we know that they actually kind of play off each other. We kind of have a dimmer switch between our parasympathetics and sympathetics. Right? It's not that we have only one part of the system active at any given time. We're thinking about what's predominating versus what is working kind of undercover. Okay. So we know that we have parasympathetic input a little bit to the heart, right? But we know that it affected kind of fewer things than our sympathetic nervous system did. So when we're talking about parasympathetic, that's our rest and digest portion of the autonomic nervous system. When we're out in the body, if we're not in the head and the neck, we're thinking about it coming from usually our vagus nerve until we get down to about here in your body, right? Pretty low down in the abdomen. So it's coming from one of our cranial nerves, traveling a long way. It's ultimately sending branches to our sinoatrial node, a little bit to our atrioventricular node. So those are part of our conductive system of the heart. And the overall effect here with our rest and digest parasympathetic branch is to decrease heart rate. Okay. So that is really the only factor pretty much here that we're thinking about in our mean arterial pressure equation. Right? We had our stroke volume times our heart rate times total peripheral resistance. So what we see here, right, is that the main way that we can affect mean arterial pressure with our parasympathetic input is we're not going to affect stroke volume. We don't have effects here on total peripheral resistance either. That was really all sort of sympathetic and hormonal stuff. But what we could do is decrease the heart rate. Okay. So if we talk about an increase in parasympathetic input, we think, okay, increase in parasympathetics, we're resting, decreasing the heart rate. Therefore, we would see a decrease in mean arterial pressure. So that's how we're thinking about all these sort of bullet points, these factors. We're just thinking about what's going to be the effect overall. Okay. So then we can go through and think about the sympathetic input. And when we think about the sympathetics, we got a lot more to think about. So the sympathetic nervous system, the sympathetic branch of the autonomic nervous system can affect each of these factors, the stroke volume, the heart rate, and the total peripheral resistance. So it's doing an awful lot. So when we talked about the heart, we saw that it also goes to our electroconductive system. So it's also going to the sinoatrial node and the atrioventricular node, helping us set that heart rate. Okay. But a special thing about the sympathetic part of our autonomic nervous system in our cardiac unit was that it can also go to the heart muscle itself. So it also innervates the ventricular myocardium, the word for the muscle of our ventricles. And what it can do there is it increases their contractility. Okay. So if we think about increasing contractility, I'm about to draw an arrow on this equation. So think about where you would draw the arrow, which of these factors we're affecting. So if we're increasing the ventricle's contraction, ultimately what we're affecting is the stroke volume. Right, they're squeezing harder. That means they're squeezing more out. So we're increasing stroke volume. So we would therefore increase mean arterial pressure, all else being equal. Okay. And we see new for this unit, right, was our understanding of the vasculature. The arterioles and the veins here are also affected by the sympathetic input here. So our arterioles, we talked about the arterioles as really varying in their resistance, right? So we talked about the fact that we can have vasoconstriction. So constriction, decreasing a radius, therefore increasing resistance, right? So before we talked about increasing resistance as decreasing flow, but now that we've reshaped this equation, you can see that an increase in resistance can also have the effect of increasing our blood pressure, our mean arterial pressure. Okay. So that's our sympathetic input to those arterioles when we have that norepinephrine binding to our alpha adrenergic receptors throughout the body. And we add it all up to get our total peripheral resistance. Now the veins was that slightly trickier part that we just started last week, sorry. All right. So we were just looking at that flow chart and we were thinking about compliance. So overall, we were thinking about compliance and the point of decreasing our compliance in the veins, increasing that venomotor tone, is that we were increasing pressure in those veins so that we have more return to the heart. When we have more return to the heart, more blood in the heart, we see an increase in stroke volume and therefore an increase in mean arterial pressure. So that's how we're thinking about like each of these effects as we step through what's going on here. So here we have an image for those of us who like pictures about our sympathetic nervous system and what it's connecting up to. So here we see that sympathetic connection to the SA node and the ventricular myocardium here on the bottom. And up at the top, we can see our vagus nerve coming in and affecting those SA node, and it would go to the AV node as well up here in the right atrium, but not reaching down into the ventricles. So we're about to think about those baroreceptors. So I want you to read these answer choices. I know we haven't talked that much about a baroreceptor. I want you to predict how that baroreceptor could possibly be helping us regulate our mean arterial pressure. Okay, so we're going to break this question down. All right, so we know we're sending signals because all of our answer choices have that. Okay, so our baroreceptor is going to send a signal. So we're trying to figure out where we're sending a signal. So we can see that these answer choices vary. Ultimately, are we sending a signal to the SA node? Are we sending a signal to our central nervous system? Are we sending a signal to blood vessels? Or are we sending a signal to ventricles? That's our first difference here in these answer choices. Okay. We've just talked about mean arterial pressure and how we change it. But what we've been talking about with our SA node, our vessels, and our ventricles, right? We've been talking about the autonomic nervous system, right? So we've been talking about the autonomic nervous system, those nerves going to all these places to change heart rate, resistance, and stroke volume. So our baroreceptors, rather than being how we send out our effect, right? Our baroreceptor is how we sense in the first place that we have had some type of change, okay? So we're going to be thinking now, here it is, right? We're thinking about the baroreceptors as being the first part of this chain. The signal that the baroreceptors are sending is, what is our pressure, right? They're asking and telling your central nervous system, what pressure do we have, so that we know what we need to change, whether we need to make a change. So we're going to have a big flow chart that we'll walk through. Okay. So our ultimate goal with something called the baroreceptor reflex is that in response to a drop in blood pressure, like when you stand up, gravity is pulling blood to your feet, we want to immediately have a reflex that pulls our blood pressure back up so that you don't faint, so that your brain is getting enough blood flow, essentially. So that's our goal. Okay. So the first thing that happens is you have a drop in blood pressure. So the most common in your day-to-day life is this sort of standing up movement. That's when you'd notice it yourself. But we can have drops in blood pressure for various reasons, like hemorrhage could cause a sudden drop in blood pressure, right? If you're suddenly bleeding out a lot of blood, there are other reasons, right, that we could see drops in blood pressure. Okay. Right. Now, the way we know that we have a drop in blood pressure is not that you're walking around with a blood pressure cuff every day. It's that we have these arterial baroreceptors. We talked about the fact that we have some in the aorta, and one in the aorta, and we have one essentially at that split in our neck, in our blood vessels, our carotids, between the internal and external carotid going up to the brain. Okay, so we have these baroreceptors. They essentially work by feeling how much stretch there is in the walls. And what they do is they're just constantly sending a signal, kind of like at a pace, right? And your brain knows that if they keep going at that pace, you keep having the same amount of stretch, you keep having the same blood pressure, right? Now, if they sense less pressure, what happens is that they slow down that pace, right? Less stretch, they're just slowing down their action potentials that they're sending up to the brain. And that is what tells your brain that the blood pressure has dropped. So when we have a drop in mean arterial pressure, those arterial baroreceptors are a little less active because there's less stretch. So they're sending lower frequency of action potentials to your central nervous system. Right. So what your brain, or your brain stem, I should say, is actually noticing is just that change in the rate of action potentials. So we want to think about what's going to happen in response to this. So take a second. All right, so we've just had this receptor bit. So we're sending up to the central nervous system. So now we're going to think about what those central nervous system control centers, those integrating centers are sending out to adjust this. Okay. So we're breaking this out by pieces. So we're going to start with the parasympathetic activity, because as we saw in that earlier summary slide, was the parasympathetic activity is a little simpler, right? We're affecting fewer things with our parasympathetics. Okay, so our overall goal with this reflex is to bring our blood pressure back up, right? I'm just gonna write our equation again because it helps me think. Okay. So our blood pressure is our stroke volume, our heart rate, and our resistance. Okay. Cool. All right. So when we're thinking about what our effects are going to be, then we want to think about how can we make our mean arterial pressure go back up, right? This is a reflex to fix this sudden drop. So to fix a drop, we're going to have to increase one or all of these factors, and we are actually going to affect all of them. Okay. So we're trying to do anything that's going to increase our stroke volume, our heart rate, or our resistance. So when we think about parasympathetics, the only one of these factors they can affect, take a second and remember, they can affect the heart rate, right? So specifically, the parasympathetics lower the heart rate. So if we're trying to get our mean arterial pressure back up, we're trying to turn those parasympathetics off, right? So we're going to lower our parasympathetic activity in order to increase that heart rate, right? When we have lots of parasympathetics at rest, we would see a drop in heart rate. So if we decrease parasympathetic activity, we're going the opposite direction. We're increasing that heart rate. Okay. So as we increase that heart rate because we're decreasing parasympathetic activity, what's really happening in the middle there is that by decreasing parasympathetic activity, our sympathetic nervous system is able to take over a little bit, or just that natural pace of the SA node, which is actually kind of fast. So we're increasing the action potential frequency in the SA node, therefore increasing our heartbeats because that's our pacemaker for how our heart is beating. So in total, that is one of the effects that's going to get us towards increasing our mean arterial pressure. So then we can step to our sympathetic activity. So the other half of the autonomic nervous system. So we are toggling back and forth between these two. So if we're decreasing parasympathetic activity, we're going to increase the sympathetics. So now we're still trying to increase mean arterial pressure. So we're just going to try and think about how can we increase stroke volume? How can we increase heart rate? How can we increase total peripheral resistance? Right, that's our goal with this baroreceptor reflex. So all we're going to do is step those out. So the first thing we can do, we got a little arrow here, right? That's sympathetic activity. We also have innervation of the SA node. Okay. So as the parasympathetic activity on the SA node is decreasing, our sympathetics are increasing. So that's upping our heart rate. Okay. But now we have some more factors that we can affect. So our next thing still has to do with the heart. Our sympathetic nervous system doesn't just affect our heart rate, it also affects how hard our heart can contract. So we increase how hard our heart can contract. We increase the contractility of that muscle, the ventricular myocardium. And that affects one of these factors. If it's not heart rate, and we're still thinking about the heart, hopefully we all got to stroke volume, which is just how much blood is coming out of the heart when we constrict that left ventricle. Right. So that's how we're increasing stroke volume. So now we got two more things to go. All right. So the next factor we're going to think about are the veins. This was the slightly trickier one, or at least I think that this is the tricky one. All right, so we say that the sympathetic activity is increasing venomotor tone, which has to do with how floppy those walls of the veins are, or in more formal terms, their compliance. Okay, so we increase venomotor tone, make them less floppy, we make them less compliant. Okay, so this is that bit about increasing return to the heart. Okay, so when we see that increase in venomotor tone, we see a drop in compliance, Therefore, an increase in the pressure, right? Because we now can't have that much volume without also increasing pressure. This increases our end diastolic volume, which was just how much blood gets into the heart at the end of its relaxed phase. So during diastole, the heart fills. If you have high pressure in the veins, that means you have a larger pressure gradient between the veins and the heart. So the heart fills more. If you have more blood in the heart, you can pump out more blood. So we increase the stroke volume. So that is again affecting this first factor here. So finally, we go to our last piece. So we're trying to figure out now, ultimately, how are we affecting our resistance? Okay. So the main way that we vary resistance is with arterioles. We talked about how we can vary resistance in arterioles to specific organ systems in order to adjust how much flow those specific organs are getting. But we can also system-wide affect your resistance. Our total peripheral resistance is just all the resistance in your body added up. So if you change resistance in the arterioles broadly, you are going to affect your mean arterial pressure. So with our sympathetic activity, overall, our effect on the arterioles, so we have that norepinephrine binding to alpha adrenergic receptors, causing vasoconstriction throughout the body. Our caveat on that, in case you're just trying to jog your memory about that set of lectures, was when we had epinephrine affecting those beta-2 receptors in the skeletal muscle in the heart, which does happen, but the vasoconstriction going to the alpha receptors is a larger effect. Okay, so vasoconstriction, constriction, smaller radius, which means we have a higher resistance. Okay, which means we are increasing our total peripheral resistance. So an increase in total peripheral resistance increases our mean arterial pressure. So that's our whole loop and why all of these effects are going to increase our mean arterial pressure. Now, once this happens, I think an arrow is going to pop on. This is a negative feedback loop, right? So all we mean when we say we have a negative feedback loop is that we had this system making changes, right? We saw an arrow signal, we saw a problem, we saw a deviation from a set point. So we're making changes, but when we are back to normal, right? So when we go back up, negative feedback, we turn the signal off, right? So once we no longer have a drop in pressure and we're back to normal, we don't have to do any of these things, right? We can stop doing all these things once we're back to our normal, regulated, expected, desired set point for our blood pressure. So questions here about this map of the baroreceptor reflex. So hopefully stepping through this kind of conceptually makes it a little less messy to look at than a flow chart. Hopefully we have a number of different ways we can think about and understand this. So that's our goal, is just to figure out how we can change that pressure, how we can get it back to normal. Okay. So that was our baroreceptor reflex. It was a response to a drop in pressure. We're increasing it back up to normal. Negative feedback loop, it turns off once we are back to normal. This is a compensation mechanism for a change in blood pressure. But if we have a long-term problem, if we have like consistently low blood pressure or consistently high blood pressure, this reflex is not going to help us. It's not going to be really adaptive, because we need to have our autonomics, our parasympathetics, and our sympathetics doing other things, right? We can't always just be using them for blood pressure. So we're going to want to regulate this long-term using other mechanisms. So specifically, what we're going to do in the long term is we're going to regulate blood volume using our kidneys. So anytime you see this word renal, right? Renal is referring to your kidneys. Okay. So we're going to have renal regulation of blood volume, which is largely going to be in unit 3 here. But for now, we just want to know that they're going to play a role there. We know sort of, we can piece together some little pieces of that. We know we're regulating volume. We know we're thinking about veins, right? Veins hold volume. We've just thought about the fact that veins can change how we're returning blood to the heart, right? So we have some sort of factors we can pull together to see kind of a big picture view of how that might work. For those of you who are thinking about that video at the beginning, this is why we saw salt coming up. When we get to the kidneys, we're going to see the kidneys are really involved with blood volume and water, but also with processing of salt, okay? So that is, stay tuned for later. At the same time as we have this neural stuff going on, we do also have hormonal control. So some of this is going to be playing into our sort of short-term regulation, and then a lot of it is going to play into that renal regulation in the long term as well. So for hormonal control, the one we've talked about the most at this point is epinephrine, right? We sort of pair up epinephrine with our understanding of the sympathetic nervous system, because the sympathetic nervous system is going into that medulla to those chromaffin cells, releasing epinephrine as a hormone that's similar to norepinephrine, okay? And we're also going to have vasopressin and angiotensin too playing a role here. Okay. So we're going to think about epinephrine as our top priority here for us. So epinephrine ultimately is going to be increasing our mean arterial pressure, right? Again, this equation for us, so stroke volume, heart rate, resistance, okay? All right, so we've talked about some of this, right? So one thing we did talk about a fair bit was epinephrine and its effect on arterioles. So our arterioles have smooth muscle. That smooth muscle can constrict. We know that epinephrine binds to adrenergic receptors, okay? So we talked about the fact that we have different effects when we have low amounts of epinephrine versus high epinephrine. With the low levels of epinephrine, we were first binding to beta-2 receptors in the skeletal muscle and in the cardiac muscle. But overall, when we have lots of epinephrine, we are also binding to alpha receptors, okay? And when we bind to an alpha receptor, that causes constriction. Okay, so our overall effect of epinephrine is to cause that vasoconstriction on the arterioles, therefore increasing our total peripheral resistance. So we do have a little shifting here as we sort of turn on epinephrine, but overall, this is the effect, okay? The epinephrine is doing similar things in the veins. So it's also sort of constricting that muscle. We now call that an increase in venomotor tone. And we've just walked through how that affects our stroke volume by helping us return more blood to the heart, therefore increasing that stroke volume every heartbeat. Okay. Epinephrine also has effects on heart rate and stroke volume at the point of the heart, right? So back in our cardiac unit, right? Overall, we're going to say epinephrine increases heart rate, increases stroke volume. So epinephrine overall increases mean arterial pressure. So hopefully we're kind of internalizing this idea that in times of kind of stress and activity, you're going to see increases in blood pressure. Right? And we maybe know that from daily life, right? Like if you go to the doctor when you're super stressed out and they measure your blood pressure, right? Might be a little high if you're afraid of a doctor, right? So blood pressure is affected by this flight or flight mechanisms, by our stress mechanisms. And this is also part of why long-term stress can affect the heart and affect your vasculature in negative ways, right? Because if you have long-term high blood pressure, that's causing stress on these tissues, okay? So we're associating anything that's sort of stress, agitation, sympathetics. Epinephrine is also called adrenaline, right? Just depends on what country you're in. We call it epinephrine here, but it's the same thing, right? So increases in blood pressure, increases in heart stuff, stroke volume, heart rate, increases in resistance, right? Everything's kind of clenching, pumping harder. So if you're gut level trying to predict answers, that's what you kind of want to be thinking about, right? Because ultimately, after we memorize facts in A&P, what we're really trying to do for you, at least my perspective, is to kind of like train your gut instinct on what's going on in people's bodies. We learn like a lot of effects here, but big picture, don't care like if 10 years from now you remember your flashcards and Quizlets from this course, but you do want to have a sense of what happens, like a sort of intuitive sense, and you can only build an intuitive sense by practicing and learning some facts first. At least that's my perspective on learning things. Okay, so our other two hormones we will talk about more with our kidneys, but vasopressin and angiotensin 2. For now, what we want to know is that overall, they're vasoconstrictors. Okay, so vasoconstrictors, constricting smooth muscle in our blood vessels. So we're increasing our resistance, total peripheral resistance goes up, so does blood pressure, mean arterial pressure. Okay. So all of our hormones that we have talked about on this list are increasing your blood pressure, right? Increasing MAP, largely through vasoconstriction. Okay. So that leads us finally to our volume receptors. So those baroreceptors in the arteries are not the only place we have receptors. We also have cardiac and venous baroreceptors that we call low pressure baroreceptors or volume receptors. So this is going to work in tandem with our baroreceptor reflex coming from those other baroreceptors in your aorta and in your carotid sinus. Okay, so this is kind of working at the same time. We just have new receptors. So we have receptors for volume in large systemic veins, right? So instead of being stretched, they're just kind of sensing how full they are, essentially. Okay, we also have them in the walls of the atria, so that top part of the heart. Okay, so when they sense a decrease in blood volume, right, this is activating receptors that are going to work in parallel with those stretch receptors in the arteries. So we have sort of multiple different mechanisms for sensing. Do we have a drop in blood pressure? So you'll also notice we've really been focusing on drops in blood pressure rather than rises in blood pressure. Right? And that's because a drop in blood pressure is for your body kind of an emergency, right? So if you have a drop in blood pressure, you're not getting blood flow to your brain, not getting blood flow, oxygen, glucose to your brain. Immediate problem, right? You're going to faint, potentially die, depending on how low that blood flow is. High blood pressure, problem long-term, right? But not kind of an immediate emergency for your body. So your body is really focused first on sensing these drops. Okay. Right. So we have some other sort of miscellaneous factors that are going to affect our cardiovascular regulatory processes more generally and our pressures. Okay. So we're going to talk about respiratory sinus arrhythmia, which has to do with breathing. It's kind of neat, right? This is more of a fun fact, in my opinion. We're going to think about some chemoreceptor stuff that'll come back as we think about our lungs as well. And we're going to mention thermoregulatory responses and responses to exercise. Okay. Okay. So I think respiratory sinus arrhythmia is super cool. To me, it is somewhat mysterious. So it is the fact that your heart rate actually changes based on whether you're breathing in or breathing out. And some of you may know this from apparently anything where you have to like get a really steady target, you control your breathing, presumably partially because of your actual movement of your chest, but also you are affecting those beats to your body, those pulses of blood as well. So when you breathe in, you actually have a slight rise in sympathetic activity. So you're breathing in, you're actually slightly increasing your heart rate. Okay. So when we increase our heart rate, we can see an increase in MAP, right? Our mean arterial pressure. When you breathe out, right? Breathing out is kind of relaxing, right? Right. So when you breathe out, there's actually a slight rise in parasympathetic activity, which has a tendency to decrease your heart rate. So this is also sometimes why, at least I think, I'm making a collection on the fly here, but when you're really anxious and you're doing breathing cycles to try to manage that, right? You are actually kind of toggling a little bit your sympathetic and parasympathetic nervous system, right? Kind of regulating that, right? So sympathetics breathing in, parasympathetics lowering heart rate, breathing out. Respiratory sinus arrhythmia. So the arrhythmia has to do with that rhythm. Respiratory because we're breathing. Sinus I can't help you with, sorry. Okay. Next, we're going to think about chemoreceptor reflexes. So we are going to think a lot about gases and blood gases when we think about what's going on with our lungs, right? Gas exchange is going to be really important for understanding why we breathe, how fast we breathe. But what we want to know for now is that we're going to have receptors that sense your gases in your blood. And specifically, they're going to be sensing carbon dioxide in your blood. Not breathing out your carbon dioxide is actually really dangerous because carbon dioxide, we're going to find out, ultimately kind of acts as an acid in your blood. Okay. So it's going to ultimately eventually affect blood pH, which can be a problem. It's another regulated variable. Okay. So chemoreceptors, chemo for chemicals, right? They sense chemicals in your blood, specifically carbon dioxide. So they're going to try to regulate that carbon dioxide level, right? We're going to see that there are going to be effects on your breathing and the rate of breathing. So ventilation is breathing, moving air in and out of your lungs. Okay. Ultimately, we're going to see that we are going to be increasing total peripheral resistance and actually decreasing heart rate. So this is going to be a little more complicated based on the equation we know right now. Right, so we don't have all the pieces of this yet. Okay. So we're just going to know for now that the effects on resistance are bigger. Okay. So for now, we're thinking when we see a rise in CO2, these chemoreceptors are going to be able to increase our resistance, and overall, in general, we're going to see an increase in mean arterial pressure. Little tricky because there is a simultaneous decrease in heart rate. We'll talk about what that is as we're talking about the respiratory system, but fact for the future, this is kind of because your heart muscle actually working, being metabolically active, affects CO2 levels as well, right? Because you produce CO2 as a waste product. All right. Thermoregulatory responses. So we are regulating temperature. Okay. Now, a thing to know about this, that regulating your body temperature is even more important to your body than your blood pressure. Okay. So making sure that you do not have a super, super high fever, you're not having heat stroke, that's going to take priority over our baroreceptor reflex, even though drops in blood flow to your brain are a big problem as well. Right? So this is another homeostatically regulated variable is temperature. Okay. Okay. So thermoregulation is going to a different part of your brain or a different part of your central nervous system. It's going to our friend, the hypothalamus. Okay. So hypothalamus sitting below the thalamus, above the pituitary gland. Okay. Ultimately, our thermoregulatory responses when we sense a increase in body temperature. We are going to try to get rid of that temperature. And the way we do that is we send more blood to the skin. So essentially we can have that heat from the blood kind of like evaporate off your skin. I know evaporation is for water, so it's not exactly the technical term, but like that's what we're thinking, right? So in order to decrease body temperature, you send lots of blood to the skin because you want to get rid of that heat, send it out into the environment. So to do that, to send lots of blood to the skin, you have to vasodilate, okay? So you have to vasodilate, which means the way we're going to vasodilate is sympathetic activity was constricting. So to vasodilate, we're going to hold back on our sympathetic activity. We're going to decrease it. So those blood vessels are going to widen. They're going to get more flow because of their drop in resistance. Okay. So this is overall going to increase heat loss to the environment as you have your hot blood in contact with the hopefully not quite as hot room that you're sitting in. Okay. So that's great. Hopefully stopping your fever from taking over. This is also part of why you sweat, right? Because if you're losing water evaporation cools you even faster. Okay. But this is a problem potentially for your blood pressure, right? So when we're thinking about our mean arterial pressure, right? So if with our thermoregulatory responses, we're trying to get rid of heat to the environment, so we're vasodilating to the skin, we're largely first going to be affecting our resistance, right? If we're vasodilating, total peripheral resistance is just all our resistance added up throughout the body. So if we vasodilated, we dropped that resistance, right? So a possible consequence here with this drop in resistance is if you have too much of a drop in resistance, you're also going to have a drop in blood pressure. So if you're feeling really hot, getting heat stroke, and you start to get sort of lightheaded, feel like that, right? Should not surprise you anymore. Now you know a little bit of where that feeling is coming from. You actually are having a drop in blood pressure because of this regulatory mechanism trying to adjust your temperature. Cool. So our final thing is just that we do have changes with exercise. Okay, so fun fact, all right. Changes during exercise affect a lot of things. So we've talked about how we have more blood flow to muscles, we have greater cardiac output. In order to have blood flowing out to your body, you're increasing your heart rate and stroke volume, right? Which are two factors that we multiply together to get cardiac output. At the same time, you're going to have slight rises in mean arterial pressure. Slight, because we increase flow to the muscle and to the heart, right? So our overall effect on that equation wasn't like too great. We had some moderating effects, one of which is our total peripheral resistance has gone down for a bit. All right, so that's it. This is kind of the low priority thing on that list, or the lowest. And we'll do a little bit about blood next time. I do think that we're gonna kind of skip a little bit about our white blood cells and stuff. We're going to do an activity for that I will send you. So, because I think clotting is more important for our purposes and a little more complicated to talk through.